So far we learned that if y is equal to f of x, and f has a continuous first derivative on the closed interval a to b, then the length of the curve from a and f of a to b and f of b is definite integral from a to b of the square root of 1 plus f prime of x to the second power dx. But sometimes calculating this is a little bit difficult, so we prefer to write x in terms of y. To find the length of x equals to g of y, when your y is bounded between two values, c and d, you can find this length using the definite integral from c to d of the square root of 1 plus g prime of y to the second power dy. Let's take a look at one example together. Find the length of the curve y equals to f of x, which is ln of x plus square root of x squared minus 1, on the interval 1 to square root of 2. So, as you know, y is equal to logarithmic function, log of x plus square root of x squared minus 1 with base e. Remember the definition of ln of x. ln of x is log with base e of x. So we're going to use this definition and write e to power y equals to the quantity inside ln, which is x plus square root of x squared minus 1. So again, ln is nothing but log with base e, and based on the definition of logarithmic function, logarithmic expressions, logarithmic equations, here you get e to power y equals to x plus square root of x squared minus 1. Now let us try to simplify this. We're going to bring everything to one side and somehow try to factor out x. E to power y minus x equals to square root of x squared minus 1. E to power 2y minus 2e to power yx plus x squared is equal to x squared minus 1. What we did, we raised both sides to the second power, and now, as you can see, x squared and x squared, they get cancel out. So you get e to power 2y minus 2, e to power y times x is equal to negative 1. Now, e to power 2y plus 1 is equal to 2 e to power y times x. So you can see, you can easily isolate x on one side. X is equal to e to power 2y plus 1 divided by 2 e to power y. So as you can see, you can write x in terms of y. You could simplify this more. You can divide the numerator and the denominator by e to power y and write it this way. X can be written as e to power y plus e to power negative y divided by 2. Why we wrote it this way? Because now taking the derivative of x is very easy. You have e to power y plus e to power negative y divided by 2. The derivative of g, or the derivative of x, is equal to e to power y minus e to power negative y divided by 2. Well, let us go back to the formula. The length of the curve from c to d is the square root of 1 plus g prime of y to the second power dy. So L is equal to, please note that we are changing the boundary when we are changing the variable from x to y. X was bounded between 1 and square root of 2. When you plug in x equals to 1, you can solve for y, and your y becomes 0. When x is equal to square root of 2, your y becomes ln of square root of 2 plus 1. And then we take the square root of 1 plus g prime of y to the second power dy, which is basically this guy here. This is equal to the definite integral 0 to ln of square root of 2 plus 1, 1 plus, wherever you see g prime, you're going to use e to power y minus e to power negative y divided by 2. And since inside the formula, inside the integral, they have 2, we have to raise this guy to the second power. And then we take the integral with respect to y. So we rewrite everything in simplified version. Please note that e to power y minus e to power negative y divided by 2 raised to second power can be written as e to power y minus e to power negative y to the second divided by 4. So e to power y minus e to power negative y to the second power from algebra is e to power 2y minus 2 times e to power y times e to power negative y, which is 1, plus e to power negative 2y. So this is your numerator here. Very good. So the definite integral. Now inside the radical, you have 1 plus e to power 2y minus 2 plus e to power negative 2y, which is this guy here, divided by 4. Then you take the integral with respect to y. But we have more simplification here. You need to take common denominator 4 here. You have the definite integral of the square root of 4 plus e to power 2y minus 2 plus e to power negative 2y divided by 4. Now we can combine 4 and negative 2. So this guy can be written as the definite integral of the square root of e to power 2y plus 2 plus e to power negative 2y divided by 4 dy, which in turn is the definite integral of. So inside the radical on the numerator, you can combine these together, which is e to power y plus e to power negative y to the second power. Then you take the square root and you divide it by 2, because the square root of 4 is nothing but 2, then taking the integral with respect to y. But note that you have exponent 2 and you have a radical, they get cancelled out. So this integral is a half definite integral of e to power y plus e to power negative y dy, which in turn is a half e to power y minus e to power negative y bounded between 0 and ln of square root of 2 plus 1, which is nothing but 1. So the length of the curve, this curve, ln of x plus square root of x squared minus 1, as x is bounded between 1 and square root of 2, is 1 unit. So again, we wrote down this function in terms of y, not x. Why is that? If you want to take the derivative of ln of x plus square root of x squared minus 1, raise it to the second power, 1 plus that, and inside the radical, it gets a little bit more complicated to do the calculation by hand. So that's why we changed this and wrote it in terms of y, not x. And as you can see, going back to elementary techniques of taking the integral, you could take the integral of e to power y plus e to power negative y, which is e to power y minus e to power negative y, then just plug in ln of square root of 2 plus 1, simplify it as much as you can, and then you get 1 as the length of the curve.